When the price is low, we can buy more units. If the price is high, we will buy less units. So the demand function looks something like this. Demand. So, for example, at this point, this is the number of units. I'm making up some numbers. Let's say 1,000. And the price is low. Let's say 10. Look what happens at this point. At this point, the price is, I don't know, 10,000. And we can only afford 5 units. So the demand function is a decreasing function. The lower the price, the higher number of units. Now, what about the supply function from the point of view of the manufacturer? Well, the manufacturer wants something like an increasing function. So they want to sell more units at a higher price. So let's say this is the supply function, which is an increasing function. And this is something called EP, the equilibrium point. At this point, everyone, the consumers and the producers, are happy. I'm going to call it A comma B. So the equilibrium point kind of makes everybody happy, A comma B. It's exactly where the two functions meet. And I would like us to determine an equilibrium point based on any function that you like to choose, any functions that you like to choose. As you see, the demand function is a decreasing function. The supply function is an increasing function. Supply increasing, demand decreasing, okay, in all of these situations. So let's choose one. I don't really like their notation. That's fine. It's okay. They use quantity Q and price P. Fine. It doesn't matter. So let's choose a situation. Let's say 81. So in 81, we're given two functions, of course. And this is on page, I think it's 61. So we have P equals Q minus 3 everything squared. And we have P equals Q squared plus 2Q plus 1. And you see the demand is decreasing and supply is increasing. They're asking us to find the equilibrium point. And remember, the equilibrium point is a point, meaning two coordinates. So this will be, according to their notation, this will be the Q, and this will be the P. So I have Q and P. So the equilibrium point is when the demand function equals the supply. How do I start? Can anyone say anything? It's okay if you're wrong. I just want to think together with you. What do you think? What should I write to get it started? Anyone, please.
Do you square demand first?
We can. Very good. We'll do that. Yes. But what will be the starting point? I completely agree. We will have to square the Q minus 3. Excellent.
You're gonna factor it
It's already factored.
or factor out, sorry.
We cannot. This is nothing you can factor out here, and this is nothing. This is my starting point. How do I write it here? Everything you said, it's just details, but we want the big picture first. What is the big picture? What do I have to write first, and then I'll deal with the minor details.
Oh, set them equal to each other.
Exactly. So, see P and P, they have to equal each other. So Q minus 3 everything squared equals Q squared plus 2Q plus 1. This is step number 1. Yes, the details, it's correct what you said. You have to expand this, true. But this is the big picture. That's how I get the equilibrium point. Setting equal the demand to the supply. I don't even care at this point which one is the demand and which is the supply. Who cares? I have to set them equal to each other. Awesome. Can anyone expand this for us? If you're still foiling it,
I got a question.
go ahead, please.
So I was writing everything down, right? But I'm confused as to what is it under the 9. Like, you see the way is that just the way you write your nines, or like is that a G? Uh, like in the second line, you see how it says P equal
They're
9
all
squared.
Q for quantity.
Okay. Oh,
And
those are
P,
Q's.
yes, I'm sorry.
Okay.
I'm
No,
sorry.
that's fine. That's fine.
And
I just
P
wanted to make sure.
is price. Sorry about that.
Okay. Thank you. I'm good.
Thank you. Good. Can anyone expand Q minus 3 for us? That was one of the reasons why I don't like that Q, but I understand why they use it. Can anyone expand Q minus 3 for us, please? Anyone, please?
Q squared plus 9.
Okay, so I guess we have to talk about this.
Minus
A minus B squared, yes, is 3 terms.
Oh, I'm sorry.
That's okay. So it's A squared minus 2AB plus B squared. And I highly recommend stop foiling this because this is beginning algebra. We are trying to move forward if possible. It's correct if you foil, but it's going to take us a long time to get to where we're going. So the first term squared minus 2 times the first times the second, which is minus 6q, plus the second term, which is 9, squared, which is 9. So this is q squared plus 2q plus 1. Good. So now we're trying to solve this equation. How do I do it? What will be the next step? Can anyone walk us through?
Combining like terms.
Yes. How do I do that?
Would you subtract the 9 from both sides?
We don't start with numbers. We always start with what we are interested in. We're not interested in 9 and 1. We start with a hardcore. So first we subtract q squared from both sides. And then I move 2q to this side, changing its sign. So I get negative 8q. And now I move 9 to the other side and I get negative 8. How much is q?
1.
Yes. So the equilibrium point has 1 for q. What is the price? How do I determine the p? So this was the q, and now I want to find the p. And that would be the equilibrium point. Awesome. How do I find the equilibrium point or the y-coordinate?
So you would input
Exactly. Anywhere. It doesn't matter. 1 plus 2 plus 1. How much is 1 plus 2 plus 1?
4.
That's it. Awesome. Great job. So the point is here. 1 comma 4. 1 unit, $4. Or maybe 1,000 units, we don't know, and $4 per unit. So just to make sure this is price per unit. Okay, perfect. So that's a demand and supply. I'm going to share my screen. And let's take a look. Any questions on demand and supply and how to find the equilibrium point?
So like, what's the function? Is there a function in particular?
Yes, you will be given the function, yes.
Okay.
The functions are given to you. Okay. So, for example, in this problem, the function is given as r of x, can be used to approximate the maximum range, r of x, in miles of the ARS-R3 surveillance radar with a peak power of x watts. Determine the maximum radar range when the peak power is 40,000 watts. Okay? Or 50,000 watts, or 60,000 watts. We're not going to graph these functions at this point. Why? Because we can only use the graphing calculator to graph something like this, but later on in the semester we will learn how to graph them step by step. So there is no need to graph right now, just simply punch it in the graphing calculator. So determine the maximum radar range when the peak power is 40,000, 50,000, and 60,000. What do you think? What needs to be done to solve this problem? Problem 87. Any suggestions? So 87, and we have r of x equals 11.74 x to 0.25. And we want 40,000, 50,000, and 60,000. So what do you think we're asked to find? Can anyone give us an idea? Anyone, please? What do you think? Who would like to give us an idea of what we need to do?
Are we just solving for x by plugging in?
Absolutely. That's all I want you to say, please. Yes, of course. So again, please always punch in the function in the graphing calculator exactly how you see it, 11.74, and then multiplied by x, put the caret. I always like parentheses, but it will work without parentheses, but I don't know what type of calculator you have. You have the function, and all you have to do is punch it in second end table. And all I have is 40,000. I have 50,000. Do not do this by hand, step by step. It's a waste of time. Is it correct? Yes, of course. But do you want to do that? I don't recommend it. So 166.03, then 175.55, and 183.74. So please remember, this is the easiest way to deal with this. Okay, so this particular section has a little bit of graphing some functions. I would like to show a couple of them that are basic functions. They're not sophisticated functions. They all come from algebra. You've seen them before. You may have forgotten them, but you've seen them before. We can solve equations, but I don't think that is a major issue. We can graph these functions if we want to do that, but again, we're going to have a big section, a big chapter in which we're going to graph. So I'm just going to graph a few functions that I think are very important, and we need to remember their shape. So, and then we can move on. So here are some graphs. One graph that is an important graph is just the basic rational function. The simplest possible rational function looks like this. Getting closer and closer to the y-axis, getting closer and closer to the x-axis, getting closer and closer to the y-axis, getting closer and closer to the x-axis. The other one that I wanted to refresh your memory on is the absolute value function. The absolute value function looks like this, like a V. This is y equals the absolute value of x. Again, the simplest quadratic function, we graphed this some time ago. Very simple is this. This is y equals x squared. We can look at the cube function, cubic function I meant to say. Cubic function looks like this. I meant to write the cube root. And also the cube function, the cubic function. Here it is. So these are basic functions that you've seen in algebra. Here it is. It's a little bit flat here. This is not something like this. So it's flat a little bit. It's just one intercept, but flat. So this is y equals x cubed. So basically, that's all I wanted to review in chapter R. I think that's all we need. But please remember these shapes. They're very important shapes.
Can you show that page, like move it down for a second, please?
Yes, of course. And also
Thank you.
remember, I will post this after class. Good. I do have a little discussion for today. For 6 little points. Let me see. From 7:45 to, yes, you have 5 minutes. You only need 1, but you have 5 minutes. Okay, so now oh, I'm so sorry. Did you need more time on this? Sorry. Did you need more time on this?
I'm good, thank you.
Okay, perfect. Thank you. Okay, so we're finally starting chapter 1. It's a big chapter. However, we are starting with a very important concept. The concept of a limit. The limit concept. Okay, so I would like us to review something called operators. What is an operator? It's a process that does something. So can anyone tell us, what does this operator do? Whatever this is, I don't care. What does this operator do? And I'll write it here. It takes or applies what? The what? How do we call this?
Square root.
Very good. Of or to, whatever. Awesome. What does this operator do? It does what to this quantity?
It cubes.
Yes. Excellent. What about this one? What does this operator do?
Divides.
Yes. One more. It applies the to, it applies what? Anyone remembers this?
Natural log.
Excellent, yes. It applies natural log. So when we see these operators, we know what they do to this. Whatever we apply it to, it doesn't matter. But we know what it does. Okay, this is also an operator. So LIM applied to a function, and of course something else follows here, but I don't want to discuss it just now. I just want you to understand only one thing at this point. This is also an operator. What does this do? It finds the tendency. It finds the tendency where the function is going. It does not apply natural log. It does not apply 1 over. It does not cube. It does not take the square root. It's totally different. It finds where this is going. When x approaches, let's say 5, this is red, x approaches 5. So this operator is telling us where the function is going, the tendency of the function, what it approaches, where is it going, which value or maybe no value, when x approaches 5. So this operator has to be understood in the same way as every other operator, but it does something else. They're all different. We never repeated anything here. This does one thing, this a different thing, this one a different thing, different operation, this one a different operation, this one a different operation. What does it do? It tells us where the function is going when x approaches 5. Okay, so let's